Now, another example I'd like to look at today is a different series. It is a power series, but it is not one that we have seen so far. So this power series takes every power of x. My coefficient is going to be 1 divided by n factorial. So bear in mind here, I'm using the convention that 0 factorial is 1. If you add up nothing, you get 0. If you multiply nothing, you get 1. Same idea. So what does this series look like to begin with? N equals 1. I'll have x to the power 0 divided by 0 factorial. That's just a 1. N equals 1. I'll have x to the power 1 divided by 1 factorial. Okay, nothing special there. N equals 2. I will have x squared divided by 2 factorial, which is 2. N equals 3. I'll have x cubed divided by 3 factorial, which is 6. And so on. So first of all, where does this series converge? Second of all, what does it converge to? Okay. Well, let's figure out its convergence first. Before I can talk about derivatives, before I can talk about functions and all that, I need to know that this series actually converges to something. So I am going to use the ratio test. Why do I use the ratio test? Because when I take ratios of successive terms of this series, those will be very nice to work with. My x's will cancel, my factorials will cancel. Just watch. So in the limit, as n goes to infinity, I am supposed to be computing the ratio of the n plus first term divided by the nth term, just like that. Now, what is that going to look like? As usual, I am dividing fractions, so I'm just going to use reciprocals instead. My n plus first term has a numerator of x to the power n plus 1 and a denominator of n plus 1 factorial. Then I have to multiply by the reciprocal of the previous term in the series, denominator x to the power n, numerator n factorial. So my integers are always going to be non-negative, I should hope, in this summation. This n plus 1 factorial is the product of all the whole numbers starting at 1 going up to n plus 1. And that's going to cancel out with all of those all of those integers in my n factorial, with the exception of n plus 1, which is too big. It doesn't have anything to cancel with when I exhaust this product in the numerator. And then I have 1 more x in my numerator than I have in my denominator. And now, in the limit, as n goes to infinity, well, eventually n is going to be bigger than the absolute value of x. And then after it gets to that point, n is going to keep getting bigger. So it doesn't actually matter what value of x that I pick. This limit, excuse me, is going to 0. Excuse me. So this limit always goes to 0, no matter what x is. But that means, I got to do my interpretation now. If the limit from the ratio test converges to a real number which is less than 1, I'm pretty sure 0 is less than 1. I'm feeling pretty strong about that today. that means that the series converges no matter what x is. So this series that I started with does define a function. I'll call it f of x, but we'll have another name for it soon enough. And this function is defined for all values of x, whatever x you want. Take 137. Then the series 1 plus 137 plus 137 squared on 2 plus 137 cubed on 6 plus 137 to the 4th power on 24. That infinite sum will converge to some number. What number would that be? Now, you might have seen this in, say, maybe an AP course or something, or maybe not. That's fine too. Let us remember, as students of calculus, we are invested in the calculus mindset. So we can find out what this function is by calculating its derivative instead. This is the strength of the calculus mindset. If I have a function I don't understand, I will take its derivative, and maybe that will help me learn more. Let's calculate this derivative. My f prime of x, I'm taking the derivative of a power series. Power series are special because it is power series where I can take a derivative by taking a derivative of just each piece of the power series separately. Once again, this is not always true. This is something that makes power series special and one of the reasons why we like power series. Okay. So I know how to do this derivative. It's just the power rule. How nice that I only need the power rule to differentiate a power series. Well, then I will have x to the power n minus 1. And I had to bring down an n. My denominator, that was really just part of the coefficient here. If you like, this is a 1 divided by n factorial. So I'm going to get cancellation there. As long as n isn't equal to 0, right? Because this derivative of this 1 up here, that's going to be 0. So let's say that this formula starts at n equals 1. Well, that's going to be n starts at 1, goes to infinity, x to the power n minus 1 divided by n minus 1 factorial. What? So what does this series look like? For n equals 1, I'll have x to the power 0, which is 1. I'll have 0 factorial, which is 1. For n equals 2, I'll have x to the power 1 divided by 1 factorial, just x. For n equals 2, x equals 2. For n equals 3, I'll have x squared divided by 3 minus 1 is 2, 2 factorial. I can't see you because this is pre-recorded, but are you feeling this existential delight that I'm trying to convey here? When I calculate the derivative of this function, again, because this is a power series, I can do this differentiation on each separate power of x. What is the derivative of 1? Is 0. What is the derivative of x? It's 1. what is the derivative of x squared divided by 2? It's x. What is the derivative of x cubed on 6? It's x squared divided by 2. The next thing in my list is x to the power 4 on 24. Its derivative is x cubed on 6, and so on. This function's derivative is itself. What function do we know whose derivative is itself? F of x is the exponential function, e to the x. That's what it is. How do I know that? Because I took the derivative of my power series and I got back the function that I started with. So something that is so special about having my factorials as the coefficients of my power series, when I take a derivative, after my cancellation and the dust settles, I've got the very same power series that I started with. And only two functions are their own derivatives. One of them is f of x equals e to the x, and the other one of them is g of x, which is just 0 everywhere. And this is not the 0 function. So this power series is its own derivative. And for that reason, this power series describes the exponential function. When I was talking earlier about what is the number 1 plus 137 plus 137 squared divided by 2 and so on, what does that series equal? Well, I picked 137 as the value for my x. So this series has to converge to e to the power 137. That's what number it is.